So after I finished the course on computing mean weighted bearings, I got some good feedback, and it related to one particular aspect that people have encountered either in an exam situation or in real life. And it's basically this question I have here on the board. What if the data is in coordinate form? If you remember, I had these monuments, I had bearings and distances, and so what if it's in coordinate form? Well, the first thing I have to say in response to that is no problem. The same principles apply, and actually it is easier, as you'll see here very soon. So we're going to work the last problem where instead of distances and bearings, coordinates are given. So here's the problem that I originally had over here. Ignore the A, B, C, D, E, F. If you ignore the A, B, C, D, E, F, you'll see it's exactly the same problem. It's from that state-specific sample exam. And we had a bearing and a distance in chains over here for the western line, and there's two eastern lines, and we had distances in bearings and chains. But what I'm saying is, what if we don't have those and instead are given coordinates? So I've erased them from the diagram, and I have here this table, this list of coordinate points. Now I had to compute these manually using the data that you just saw, and I had to also manufacture data for BC and CD. And if you're ever curious about what the manufactured data is, calculated by hand, and send me an email, I'll be happy to tell you if you got that correct. But this is very standard inversing, so really I don't think any of you need that practice, assuming you've been practicing inversing. So I assumed B as being 10,000 feet, and then applying the bearings and distances that were given, I could calculate the coordinate of A. Obviously I've gone north, and as you can see, it's going westwardly. The easting is slightly smaller than 10,000, so that must be a northwesterly bearing, and if you go back and look at the original data, you will see that. Then I had this manufactured bearing and distance for BC and CD to get to point D. And so I have the coordinates of point D, and then the important ones are the bearing and distance to get to E. And again, I'm going north, and if you look here, 15,334 versus 15,328, we drop slightly, so D to E is to the northwest. And then finally, if you remember this, E to F was due north, exactly due north. So there's no change in easting, and obviously we went north. So you'd be given a coordinate table. You might have to calculate a few coordinates maybe. If it's a blended problem, that gives you some distances and bearings and some coordinates. So we have the same kind of table, but instead I put in here delta northing and delta easting, and I've shown the arithmetic we use to get the latitude and departure. And hopefully you all realize that a delta northing is nothing more than the latitude, and delta easting is nothing more than the departure. So we got 14,880.63 minus 10,000, so that's 4,880.63. That's easy, I can do it in my head. You bring up the calculator because I'm subtracting a larger number from a smaller number. So here we have 9975.273 minus 10,000. And we get a negative 24.727. All right, now let me get rid of the calculator, because I'm hoping with this one example you understand the process. You would do the same thing with the other coordinates here to get these results. And then when you add up the latitude and departure columns, you get the 7395 0.889 for the northing of this combined line, and a negative, meaning to the west, 30.416 for the departure. So then, if you look at that line, obviously the angle is exaggerated because it's a fairly tiny angle, but the 30.416 is this distance here, and of course the 7395.889 is the longer north-south direction to get that red line, which is our line of interest. And as you know, the length of the line is not important, but the bearing is, the bearing angle. So the bearing angle is exactly the same equation as we used earlier, except the numbers are negative 30.416 over 7395.889. And if you go back and compare, you will see that after the equal sign, it's the same thing. It's 0.23563 degrees or 14 minutes and 8 seconds. So the answer is north 0 degrees, 14 minutes, 8 seconds west. So that's pretty much it. Now, the one thing I just want to point out while I'm on the subject is you may have noticed when I did it with chains that I carried the decimals out about 5 places, because chains are basically a factor of 66 smaller in magnitude, so you want to carry more resolution in the math to calculate this tangent. But here we're working in feet, so I probably didn't even need to carry it out 3 decimal places, but I did just to be on the safe side. Still want to carry out a few decimal places more than you might need on the decimal degrees before converting to 14 minutes and 8 seconds. It's actually 8 and some change seconds, but generally on most exams, unless it's more of a control surveying or geodesy type question, it's not likely they're going to ask you for what the decimal seconds in a particular angle or direction are. So that completes this whole topic of computing weighted mean bearings. And I just want to add with perhaps this general advice. So let's say you have 2 lines, and let's make it a river again, but it can be a fractional section for whatever reason. And you have bearings or coordinates or whatever, but you can compute essentially what the vector sum of these 3 are. So let's say this line is a little bit to the northwest. Let's say this line is a little bit to the northeast, and this line is a little bit to the northeast. So if we put them end to end, what you have is this line to the northwest, this line to the northeast, and this line to the northeast. And what you're doing is combining them, and you're weighting it by the lengths of these lines. And that's what you're after, not the length, but the direction of that particular line. And that's what a vector sum means if you studied vector algebra. So with that, we will end this particular course.